We've talked about what exponential functions look like. An exponential model is going to be a way for us to represent some sort of real world phenomena using exponential growth and exponential decay. When we're talking about logistic models, there's two models that we use, or there's two equations that we use. The model that we're going to use the most is going to be C over 1 plus A times B to the X. You can use the A times E to the KT, negative KT, but generally this one is going to work a little bit nicer, at least to start. Today, though, we're going to focus on just exponential models. So exponential growth and decay is usually described using percentages. And we always write percents in math as decimals. So that means we always want to move the decimal place 2 places to the right. Uh, when we're talking about exponential growth, we're going to have an equation like f of x equals p times 1 plus r to the t. And for decay, it's going to be p times 1 minus r to the power of t. So in both of these, r is going to be our rate of change, which in this case is going to be growth or decay. And P is going to be our initial amount. We use P to stand for principal, which is primarily a term used in banking examples, but it's going to hold true for banking or population or half-life or anything like that. Let's look at an example where we're going to look at exponential growth and decay through the lens of cancer research. So this is something that when we're looking at clinical trials, we often want to compare not just to a placebo effect, but we also need to compare to previously known medicines because that's going to help us know whether or not the side effects of some treatment are going to be worth it for a new treatment because it may be better than nothing, but it may be more detrimental than others. So we're comparing, in this case, 3 different hormone replacements or hormone therapies for non-metastatic cancer. So looking at this problem, we have that a researcher at the Fred Hutchinson Cancer Research Center is exploring the effect of a new hormone therapy for estrogen receptor positive tumors. The researcher compares the rates of 3 preoperative non-metastatic tumors. When we talk about preoperative, that means that these are tumors that potentially will be removed through surgery, and non-metastatic means that these are tumors that have not spread. They're still in their initial location in the body. The first tumor in the control group is being treated with a standard dose of 20 milligrams of tamoxifen, which is being administered daily, and it's decreasing the diameter of the tumor on average by about 0.434% daily. The second tumor in the control group being treated with a daily dose of 1 milligram of anastrozole decreases in diameter by 0.465% per day. And the tumor in the test group with the new drug is exhibiting an approximate diameter decrease of about 0.48% daily. The drug is approved for human trials on preoperative tumors that are too large for lumpectomy. 3 comparative patients are administered standard doses to reduce tumor diameter from 3 centimeters. Lumpectomy surgery is not recommended for tumors measuring 2 centimeters or more. So what we want to find out is using each of these 3 medicines, what would be an approximate timetable for surgery so that each of these patients could partake in a lumpectomy to remove the tumor. So we're going to look at this by creating models for each of these 3 drugs. So here we have a table that we're going to put together that is going to tell us what our model is and how many days to a T1 grade. T1 is a size of tumor, and those would be tumors that are small enough for a lumpectomy in breast cancer. The first example we have here is the tamoxifen. So with the tamoxifen, I'm going to call that D sub T for tamoxifen. So the diameter of tamoxifen at time t equals, we're going to start with our initial rate, our initial diameter. Remember, our first diameter for all of these tumors is about 3 centimeters. So I'm going to say that this is 3 times, because we are decreasing the size, we are making these drugs are making the tumors smaller. What we're going to have is 1 minus my 0.434%, so that would be 0.00434 to the power of t. For my second control, anastrozole, I'm going to call this one d sub a of t, and that's going to equal 3 times 1 minus 0.6465% is going to be 0.00465 to the power of t. And for our new drug, which is a fictional one that we're calling estrofen, estrofen is going to decrease the diameter d sub e of t equals 3 times 1 minus 0.0048 to the power of t. So what we're going to do now is we're going to go through and we're going to find out what t would have to be to get down to a size T1, which would be under our 2 centimeter diameter. With this, I want to find out when that's going to equal 2, because that's the first point where we could do our lumpectomies. So what I'm going to set up is I'm going to replace all of my diameters with 2, and I'm going to solve for t. We could go about this in multiple different ways, including graphing and finding where that's equal. We could use our calculator to use some of the value function pieces. But this one, I just want to figure out algebraically. For each of these, I want to get the exponential piece by itself. So I need to get rid of those 3. After that, I need to get that t out of my exponent, so I'm going to use ln. If I take the ln of both sides, go ahead and divide everything away so that I have t by itself. where of how long each of those is going to take. So we can say with this new drug, even though the rate change wasn't that much, 0.48 versus 0.46%, we can see a pretty sizable difference between the anastrozole, the tamoxifen, and the estrofen, so that we can make a better idea, a better informed judgment as researchers to see which one would be more effective. Here's an example for you to try out on your own. We're looking at money markets and how we can compare investments to inflation. Remember, when we're talking about inflation, let's think about how much that 17 million would grow if it was increasing at the rate of inflation, so that we can compare uh, how much that 17 million is after that 3 years of inflation. So for this first one here, we want to take that $17 million and we're going to use this 0.17% interest rate and a maturity term length of 3 years, which means that we have to keep that money in that CD for 3 years. And at that point, we can pull it out. So a CD is kind of like a savings account that you can put money into. It's stuck there for a while, but it's kind of like a guaranteed investment. So with this example, we have a monthly interest rate of 0.17%. So I'm going to start with my principal balance, $17,362,223 times, because this is a savings account, it's going to grow money, 1 plus 0.0017. And then in 3 years, we're going to have a total of 36 months. So when I go ahead and plug that into my calculator to figure out how much money that would be worth, what I'm going to end up getting would be approximately $18,457,020.13. If I think on that same front about the inflation rate, I'm going to have a very similar equation, but this one's in years and not in months, and my rate's a little bit different. So I'm going to start with that same principal number. I'm going to multiply by 1 plus 0.012. And this one, instead of being to the 36th power, is just going to be to the third. And we're going to end up getting 994, sorry. 994,793 and then 51 cents. So here we can see that, we exceeded inflation. We made quite a bit more than what we would have lost due to inflation, but we're still not looking at a very high yield. We're only looking at about 2.04%. So the worthwhileness of the investment is up to you, but I would say, since we did beat inflation, it's at least a sound investment. It would be better than putting your money in an account that has no yield whatsoever.